All right, now you might have been wondering how is Hooke's law, which is that you're applying a force to an object and then it's got this constant, the spring constant, and then it's going to stretch a certain distance. So let me use the letter R instead of the letter L for the distance that it's going to stretch. And then also there's a minus sign on there. And so the minus sign means that if your force is pulling on a spring, what does the spring do? The spring pulls in this direction on you, in the opposite direction. If you've got a spring and you push on it, what does the spring try to do? The spring tries to push backwards. So that's what significance of the negative sign there is. So I wanted to show you how this formula is related to the atoms that makes up the spring. And so we also had this other formula, so this is going to be Hooke's law, this one here, but we also had Coulomb's law. So we learned this in electricity, that Coulomb's law depended on a constant, and so this was called the electrical constant that depended on the material, and then it would depend on charge number 1, and then charge number 2, and then the distance between them squared. So this was Coulomb's law for electricity, and then this is Hooke's law for a spring. And I wanted to show you that those two things are related to each other. So imagine that you've got two atoms, and so I've got one atom that has a positive nucleus and then a single electron that's in orbit around it, and then over here is another atom that has a positive nucleus and then a negative electron that's in orbit around it. So imagine two atoms. The electrons on each atom will be attracted to the nucleus of the other atom. Opposites attract. So the graph shows how the force would change according to Coulomb's law. So notice that the closer the electron gets to the nucleus, the stronger the force gets, because as the distance gets smaller, as r gets smaller, then F gets larger because it's in the bottom part of the formula. But that's not the whole story, because but the positive nuclei would repel each other. So you got the protons in the nucleus of this atom are going to be seeing the protons in the nucleus of this atom, and they don't like each other. So like charges are going to repel. So there's the graph that's going to show the force versus the distance using Coulomb's law again for the positive nucleus versus the other positive nucleus. Now what we want to do is put the two graphs together. So we're going to take this graph, which is the attraction for the electrons on the protons, and then we're going to take this graph, which is the repulsion of the protons on the protons, and then we're going to put them together, and then you end up with this graph here. So you notice that it has elements of both graphs on it. So when it's really, really close, you notice that it's going to be repulsive. The closer those nucleuses get to each other, the stronger the force of repulsion is going to be. So that's the first part of that graph. Then the second part of the graph, when you get further away, then it's attractive because of the electrons on the protons. And so notice that there's a sweet spot. So where the graph crosses the axis, so right here, notice there's no net force acting on the electrons when you get there. So that's going to put a certain distance that the two atoms are going to want to be away from each other. Now, if you push them together, okay, if you try to push them together, then you're going to have a force that's going to be repulsive, and it's going to depend on the distance. If you try to pull them apart, then there's going to be a force on it trying to push them back together again. So we can actually derive this equation right here through the use of Coulomb's law. Pretty good, eh? All right. So let's take a break, and when we come back, let's talk about a quiz.